So wait a moment as we get the question onto the slide.
So it looks like that there was a tie for 13 and 14. I think I'll do the number 14 instead, because that was, in my opinion, it's a trickier problem. So this was problem 14 from last time. It's similar to a remainder theorem question. We want the remainder when x to the 28th plus 1 is divided by x to the 4th plus x cubed plus x squared plus x plus 1. So is there anything nice about the divisor, the polynomial that we wish to divide by? Yeah, so x to the 4th plus x cubed plus x squared plus x plus 1.
Terms.
Sorry, I heard somebody.
The x to the 28 plus 1 is just 2 terms.
Yep. So now we notice that the divisor is actually a factor of x to the 5th plus 1. So we can write, we want the remainder when x to the 28th minus 1 is divided by x to the 5th minus 1 over
x to the 28 plus 1.
Oh, x to the 28 plus 1? Okay, small sign. Yep, so we want this. So let's first find the remainder when it's divided by x to the 5th minus 1. Then we can get some more information about what the remainder is divided by the x to the 4th plus x cubed plus x squared plus x plus 1. So we want to write x to the 28th minus 1 is equal to x to the 5th minus 1 times a quotient q of x plus a remainder r of x.
Daniel, again, x to the 28 plus 1.
Oh, yes, thank you, Brian. Okay. Well, one thing we can do is we can write x to the 28th plus 1 is x to the 28th minus x to the 23rd plus x to the 23rd minus 1.
Plus 1.
Oh, yes. Okay. And this is nice because x to the 28th minus x to the 23rd is actually divisible by x to the 5th minus 1. So now we can subtract that. And now we want the remainder when x to the 23rd plus 1 is divided by x to the 5th minus 1. But if we do the same logic again, where we write this as x to the 23rd minus x to the 23rd plus x to the 18th plus 1, we now want the remainder when it's divided by x to the 18th plus 1. And we can continue this chain, dropping the exponent of x to the 28th plus 1 by 5 every time, all the way down to x to the 8th plus 1.
Yeah,
one step,
Daniel,
yeah?
in the third to last line, I think it should be x to the 23 minus x to the 18 plus x to the 18 plus 1.
Oh, yes, that's true. My bad. And for the last step, we take x to the 8th plus 1 to x to the 3rd plus 1. So now we know that we now just want the remainder when x cubed plus 1 is divided by x to the 5th plus minus 1. But this is just x cubed plus 1. And actually, since this thing has degree 3, we know that it's also going to remainder when we divide it by x to the 4th plus x cubed plus x squared plus x plus 1. So essentially, we can write x to the 28th plus 1 is equal to x to the 28th minus x to the 23rd plus x to the 23rd minus x to the 18th, and so on, until we get plus x cubed plus 1. So now we know that we see that every term in the sum is divisible by x to the 4th plus x cubed plus x squared plus x plus 1, because every term is divisible by x to the 5th minus 1. So now every term except the last is divisible by x to the 4th plus x cubed plus x squared plus x plus 1. So the remainder is just x cubed plus 1.
Daniel, I think you have an extra plus sign.
Yeah, I just noticed that. Well, wait. So about the 5th roots of unity, yeah, actually I think that works. I thought it was more complicated than that, but no, I think it should work. I think it might actually need to be a little more detailed than that, because you know that the polynomial is going to have degree at most 3. So you have to solve for 4 coefficients, and that means you need to throw in 4 5th roots of unity in order to get it. Any other questions on this problem? I guess I'll hand it over to William for the shortlist 2005 problem.
Let's do this question one moment. The formatting seems a bit off. That's fine. So, does anybody have any ideas for this question? In particular, what do the expressions remind you of? In light of the fact that last class was polynomials.
Vietas.
Yeah, it looks exactly like Vietas. So with this in mind, we'll try to construct some polynomials such that we can get these sums of products. So let's first consider P of x is equal to x plus a times x plus b times x plus c, and Q of x is equal to x minus d times x minus e times x minus f. So what's an easy way to get all of the expressions which we see inside this question? Yeah, subtract. So we're just going to subtract these two. So we get P of x minus Q of x is going to be equal to a plus b plus c plus d plus e plus f times x squared plus ab plus b x squared plus ab plus bc plus ca minus de minus ef minus df times x, and then plus abc plus def. So what we get. Okay. So now we see that every single term in this expression is actually divisible by s. So this means that whatever I plug into for x, the right-hand side is always going to be divisible by s. Does this make sense? So what's the convenient value I can plug in for x, which will make the right-hand side nice? It may be helpful to look at the factored form. Yeah, Kevin says f, we can plug in f. So what happens when we plug in f? We want p of f minus q of f. So now p of f is going to be a plus f times b plus f times c plus f. And then q of f is going to be 0 because f is the root of it. So now, because s divides everything, we know that f has to divide a plus f times b plus f times c plus f. So now how can we use this to prove that f is composite? Okay, so maybe you guys have seen this before. If s is actually a prime, then we have to have that s has to divide one of the 3 factors on the right, since we can't split up primes to divide everything. But s actually can't divide any of the 3 factors on the right because, yeah, as Kevin says, s is greater than all the factors. So it can't divide any of them. Hence, it can't be prime. So now we're actually not done. We need to prove that s can't be 1. But since s is at least 6, yeah. So it looks like s is composite. So that's the question. So that's it for our homework review for today. If you guys want to, so if you guys do the homework for next class, we can discuss more questions for next week. So that's it. Now we're going to go to the actual lesson.
Yeah, so I guess we'll get started with today's lesson, which is on equations. So this is probably this is a very broad topic, obviously, which is why we'll probably be having a second class on it. And well, it's basically if we have a set of equalities that all have to hold, and then given this set of equalities, we have to determine something about the variables, right? So the systems can be linear or they can be nonlinear, right? So there's just a lot of techniques that we'll have to go into, because it's hard to say anything in general about all of them because there's just so many different types of equations. So with that being said, I guess we'll move on to our first question.
Oh yeah, just a quick aside. So this week we're deciding to focus more on motivation due to responses from our feedback form. And the feedback form is meant to make this class better. So if you haven't done so, please take a moment to go to the website and complete it. Thanks.
So here's the first problem for today. And you just have to find the solutions in X for that 6th-degree polynomial.
Factor?
Yeah. What?
Try to factor.
Well, so if you look at it as it is, it's gonna be a little difficult to try to factor it because there's no clear factors right now, right? So maybe we want to try to make it look nicer before we can factor it. So yeah, Kevin had a good idea of what if we let y equal 2x, right? And if we let y equal 2x, um, well, I mean, this simplifies things, right? So, because we see that, well, a lot of these coefficients, especially like the bigger x coefficients, like the x to the 6th, the x to the 5th, they have a lot of 2's in them, right? So essentially, if we can simplify it by getting rid of these 2's basically, then, well, that'll be nicer, right? So, well, what do we get when we have that y equals 2x? Well, we just replace all the 2x's with y's, and then we get this new 6th degree polynomial. Yeah, there. Right, so, well, this looks more manageable, right? The coefficients are all smaller, right? Now, how would you go about solving this one?
You use the binomial theorem?
Well, the binomial theorem only really applies when like you have those binomial coefficients really, and you don't really see that much of that here, right? So instead, well, you do see, which I guess like you also has in common with the binomial theorem, that the bigger degree coefficients and the smaller degree coefficients are all going to be, they're the same, they're symmetric, right? So, well, we want to somehow take advantage of this, right? So, well, how would we do this? Well, essentially the idea is we want to somehow like center it so that it's symmetric about the degrees, about the constant term, right? So yeah, so what if we tried that? And now we divide everything by y cubed, right? And when we divide everything by y cubed, what do we get? We get something that looks like this, right? And if we group the similar terms together, we get this nicer expression, right? We get this equation. And well, now how would we go about solving this new, well, it's still the same equation, but we want to somehow manipulate it so that it's easier to deal with, because it's still a 6th degree polynomial, right? But it's still, we do have that symmetry, right? Yeah, so we do have y plus 1 over y. So we look at each of those 3 terms that involve y, right? Well, y cubed plus 1 over y cubed, that can be expressed as a function of y. Y squared plus 1 over y squared, that can be expressed as a function of y. And y plus 1 over y can also be expressed as a function of y plus 1 over y, obviously, right? So we essentially make this substitution of z equals y plus 1 over y in order to try to reduce the degree, right? Because in the end, like solving polynomials, a lot of the times you want to like reduce the degree so that why did that happen? Oh, that's why that happened. So we want to reduce the degree so that because in general, lower degree polynomials are easier to solve than higher degree polynomials, right? So, well, we make the substitution, and then we have this. We can, if we make z equals y plus 1 over y, we get that this equation is true. Right? Do you guys see where each of those terms came from? Yeah. Where? Yes, you are correct. That should be a z. Yeah, so so do you guys see where, yeah, you guys, I hope, see like that y cubed plus 1 over y cubed. Like if you take y plus 1 over y, cube it, and then subtract 3 times y plus 1 over y, the 3 times y plus 1 over y term will cancel, and then what you're left with is what you want. right? So that's the general idea. And well, now we just have to expand this cubic and solve the cubic, right? And well, how do we do that, right? Well, we get to, nope, that's not right. There, yeah. We get to this cubic, right? And then we want to see how, we want to solve this cubic, right? Well, do you guys have any ideas for how to solve this cubic? Yeah, you basically just start trying roots, right? So I'll sort of skip over the trying the incorrect roots, and let's just try let's happen to try z equals -3, -4, or 5, right? So we see that those are our three solutions. You can get there with enough guessing, but we see that it can factor into this form, right? So, well, in an actual contest, you know, like you just start out with the smaller roots, try ±1, see that those clearly don't work. ±2 kind of don't work either. And then you try ±3, and -3 works. And then once you get one of them, then it's easy to like finish from there, because you can just use quadratic formula or whatever on the remaining quadratic. Right, so now you have this, you have the possible values for z essentially now. Right, so now you remember that you want your equation still in x, right? So you go back step by step, and then you see, well, what can y be? Well, y can be one of these 6 values, right? Yeah, I kind of skipped a step by just using the quadratic formula. Basically, like the first set of solutions is y squared plus 3y plus 1 equals 0. Then we have y squared plus 4y plus 1 equals 0, and y squared minus 5y plus 1 equals 0, right? Corresponding to each value of z, right? And well, we remember that y is still not what we wanted to solve for. We wanted to solve for x, right? This might get cut off. No, we good. So we now just have to divide everything by 2 to get the possible x values, right? So those are the possible x values. And yeah, does anyone have questions on that? The the general takeaway from this question is well, the substitutions in general, but in particular, if you have like a symmetric equation in like such as the second bullet point, the key takeaway is like you can do this z equals y plus 1 over y substitution, and then this will like basically have the degree, right? We started with a degree 6, and then we ended with a degree 3, right? And then this will just make things easier to like factor or whatever you want to do with a polynomial, right? So if no one has any further questions on that question, I guess we can move on to the next question. Yeah. So I guess we'll move on to this question. All right. So I'll let you guys look at it, think about it for a bit, and then maybe suggest ideas in the chat. Yeah. Um, yeah, well, so the general idea is we want to factor, right? And but like it's not immediately obvious how we would factor this, right? But like we do see, like we do want to like somehow make it so that we can factor it, right? So well, we see that we have this nice like geometric progression in the middle, right? Like those odd terms, x to the 5, x to the 3, and x right? So, well, if we can like group these together, well then maybe we can get something out of that, right? So what can we get out of that? Well, so yeah, we noticed that there's some structure here, right? And well, what can we do with this structure? Well, it's a geometric progression, right? So we want to we want to like simplify this geometric progression, and maybe so we can get something nice out of it, right? Um, and well, yes, it's also a difference of cubes. I guess. Well, yeah, the difference of cubes is just a geometric progression of length 3. It's like the same thing here, right? So yeah, we're also more so focused on motivation because I mean, just knowing the answer isn't going to like knowing the answer to this question won't help you with any other questions, right? Like you want to take this question and be able to apply its principles to other questions, right? So what well we look at this and what can we see out of this new representation of the question? In particular, we see that we essentially have these two groups of terms, right? We have this 2000 x to the sixth minus 2, and we have this x times 1000 x to the sixth minus 1 over 10x squared minus 1, right? Um, so, it's fine. The yeah, let's try factoring 2 out of this first term, I guess. Um, uh, hold on. There. Yeah, so maybe like let's look at this representation now. Do you guys see anything there? Yeah, this is on overleaf. We're just using LaTeX here, yeah. Uh, so yeah, we can factor a 1000x to the sixth minus 1. Well, we can't exactly factor that because we still would have stuff in the denominator. But what we can factor is we can factor out the fraction 1000 x to the sixth minus 1 over 10x squared minus 1, right? Um, because, well, in general, we don't want fractions, right, when we factor stuff out. But, yeah. So I missed the minus 1 there. Um, there should be a minus 1 there. But, yeah, now, we now have we now factor this out, right? And when we factor this out, we get this quartic that we have here multiplied by this quadratic, right? And well, we want to consider the real roots only, right? So we think about which one of these terms is going to have the real coefficients, the real roots, I mean, right? And well, yeah, someone said we solve for that. The real coefficients are going to be in this quadratic, this second quadratic, right? Um, so we can kind of ignore we see that the first one has no real roots, right? Maybe just like see each of the first two terms is always non-negative, and the third one is always positive, right? So this is never 0. And then so the quadratic is what we want to care about. And we just use the quadratic formula on that, and we get the answer that someone said earlier, which is confirmation that we both got it right. So yes, that is our answer. Yeah, I mean, Descartes' law of science is not especially useful here, but it does tell you about the roots of the signs of the roots, I suppose. But it doesn't actually tell you anything about the actual roots, so like it's not particularly useful. But I suppose, I suppose it does tell you that you have no real roots to the quartic, which is useful. Yeah. That it does tell you. Because essentially we see that there's no positive roots, and then when we plug in negative x, we see that there's no negative roots either. Right? And 0 also clearly isn't a root. So yeah, we can use Descartes' rule of sign there, but we can also just look at the quadratic and see that that has 2 real roots. And the question tells us that we only have 2 real roots. So that also works. But anyway, that's the question, and then we got the answer is just 200 there.
Okay, so we thought that the homework part of the lesson would take slightly longer, so we actually have a 5-minute break right now. So we'll reconvene in, I guess, 5 minutes. If you have any questions, you can post them in the chat.
Okay, so this is our question now. So now we're going to be looking at multiple, like equations with multiple variables. So here we have a, b, x, and y, and we have 4 equations for them, and we need a times x to the 5th plus b times y to the 5th. So I'll give you a few minutes to think about it. Okay, so when we look at these equations, so a natural idea might be trying to multiply some of these equations in order to get like the right exponent for x. Like for example, you might try multiplying the second equation with the third equation to get x to the 5th and y to the 5th. But this doesn't seem very promising because when we multiply these 2 equations, you're going to get an a squared term and a b squared term. And you just want a and b in your final expression. So someone said that, so someone said in the chat to try multiplying the first equation by x plus y. So this looks pretty good because we can try to get the next like exponent. So first, like if you look at this, we have like a times x to the n plus b times y to the n for n going from 1 to 4. So one thing that you might ask is how to go from a times x to the n plus b times y to the n to a times x to the n plus 1 plus b times y to the n plus 1. And so to do this, So the idea would be, so you want to multiply by an x so that you get an extra factor of x in the first term, but you also need to multiply by a y in the second term. So the idea that that we want to try is actually multiplying it by x plus y, as someone suggested in the chat. So if we do this, it's one of the terms is going to be a times x to the n plus 1, and one of the terms is going to be b times y to the n plus 1. So if we finish the expansion here, so this is what happens when we expand the so this is what happens when we expand this product. So as we wanted, like the first two terms that's what we wanted, and the second two terms, so the second two terms, you'll notice that they're both divisible by xy. So we can try to factor that out here. And so if we try to factor that out, that's so this is what happens when we factor it out. And so this equation is pretty good. So, well, we can rearrange this equation first. And so now we have this. And this equation is pretty good because we can, so we have ax plus by, and then we have ax squared plus by squared, and we have ax cubed plus by cubed. So we have some sort of recursion here for the terms in that sequence. And so we have the first four initial terms. So we can use that to find what x plus y and xy are. So let's let s be x plus y, and we can let p be xy. So if we look at that equation with n equals, so if we look at that equation with n equals 2, so we have ax cubed plus by cubed equals x plus y times ax squared plus bx squared minus xy times ax plus by. So if we substitute the values that we know there, we get 16 equals 7s minus 3p. And for n equals 3, the same equation becomes 42 equals 16s minus 7p. So now we have two equations for s and p. So I'm sure all of you can solve for s and p. So we can either, so I guess we can either substitute or eliminate one of the variables. And so our solution for s and p is s is negative 14 and p is negative 38. So now we can just use this recursion to find the next term, which is ax to the fifth times ax to the fifth plus by to the fifth. So if we use the same recursion that we derived up there, it's negative 14 times ax to the fourth plus by to the fourth plus 38 times ax cubed plus by cubed. And so if we plug in the values that we were given, that's equal to 20. So that's the answer. Does anyone have any questions?
Yeah, it actually is true that this question appeared on HMMT a couple years back from 2008, and it actually has the same numbers, which is really interesting.
Yeah, so it looks like this question is good. So let's move on. So remember like the motivation that we used to find like to derive that identity here. So if you really think about that motivation, it's going to be helpful in the next question. So our next question is this Mildorf-Mock-Amy problem. And so we're given a plus b plus c, a squared plus b squared plus c squared, and a cubed plus b cubed plus c cubed. So I'll give you a few minutes to think about it. So the first thing in this question is that it's going to be hard to get some specific factorization that's going to work here, because like it's the seventh power, so that's pretty big. So you might have seen some type of factorization for a cubed plus b cubed plus c cubed minus 3abc or something like that. So we're going to use that later in the solution, but I'm just noting that it's going to be hard to use such a factorization here initially. And so some people mentioned Newton sums in the chat. So so we're just going to go through the process of deriving those relations. And so first, a little bit of notation so that I don't have to keep writing out it all the time. So we're just going to let Sn be a to the n plus b to the n plus c to the n. And we're given S1, S2, and S3. And so, as I said, it looks like a factorization for that may not be that easy to find. And so we're going to resort to what we used in the previous problem. So let's try to get a similar like recursion for Sn. So does anyone have any ideas for how to get Sn plus 1 from Sn? Yeah, so what Eric said, we're going to multiply it by a plus b plus c. So the reason we do that is because it's going to so it's the same idea as before. We're going to increase the exponent in a, b, and c. But what happens here is that we get a lot more terms than before. So now we have, so if we multiply Sn plus c, we get S plus 1, and then we get 6 more terms after that. And so does anyone have any ideas for how to relate the last set of terms on the right side? Yeah, so someone says factor out AB plus AC plus BC. And so the reason we would actually think of that is that, so every term on the right side has degree n plus 1. And so, so we already have an Sn term. So we're trying to write this term on the right side in terms of Sn minus 1 and smaller terms. So we're looking for some degree 2 term to multiply by Sn minus 1 to get terms of that form on the right. So a natural degree, like symmetric polynomial that we'd use is AB plus BC plus CA. And so now let's go and see what happens when we multiply Sn minus 1 by AB plus BC plus CA. Brian, it's on the next slide. Yeah, so we are basically just deriving Newton's sums here. But this is how you would go about finding it, yeah. So if we expand this, so I first grouped out the terms that we had on the right side before. So we have a to the n b plus a to the n c plus b to the n a plus b to the n c plus c to the n a plus c to the n b. And then we have 3 more terms here. But notice that all 3 of these terms are divisible by a, b, and c. So we can factor out a, b, c from all 3 of those terms. So if we factor a, b, c from those 3 terms, it's just a to the n minus 2 plus b to the n minus 2 plus c to the n minus 2. So that second grouping on the right side is just ABC times S of n minus 2. So, so yeah, the left side was what we multiplied AB plus BC plus CA times Sn minus 1. The first grouping on the right side is, so on the previous slide, we had A plus B plus C times Sn equals Sn plus 1 plus those 6 terms. So these 6 terms have the sum A plus B plus C times Sn minus Sn plus 1. And as we said, the second group was ABC times Sn minus 2. And so if we substitute all of those into the equation, we get this relation here. And so we were trying to write Sn plus 1 in terms of smaller Si. So we can rearrange to move Sn plus 1 onto the left side and then move that other term onto the right side. So we get this after rearranging. And so, as many of you said, so this is the Newton sums relation here. And so now it remains to determine what those 3 coefficients are. We already have A plus B plus C is 1, but we need AB plus BC plus CA and ABC. So AB plus BC plus CA is just, so we just take A plus B plus C and we can square it and subtract A squared plus B squared plus C squared and then divide everything by 2. So yeah, that one should be easy enough. So we get that AB plus BC plus CA is just -1. And so now we just have to find ABC, and we're going to use the factorization a cubed plus b cubed plus c cubed minus 3abc equals a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca. And so this is a pretty important factorization to know. And the reason we're using it is because we're given a cubed plus b cubed plus c cubed and a plus b plus c and a squared plus b squared plus c squared plus ca. So if we plug in what we know, we get 7 minus 3abc equals 4. So abc is just 1. And so now we can rewrite our recursion with the numbers that we have. And so our recursion is just Sn plus 1 equals Sn plus Sn minus 1 plus Sn minus 2. And so now we have S1, S2, and S3, and we just need to determine what S7 is. So we can just use the recursion 4 times to get S7. So S4 is 11, S5 is 21, S6 is 39, and S7 is 71. So that's the answer. Does anyone have any questions? Okay, so it looks like there are no questions. So I think now it's William.
So continuing with the symmetric system of equations with multiple variables, this is our next question. I'll give you a few minutes to look over it. And since these questions are all like pretty similar, like a lot of the methodology we learned above still applies. And I hear some people saying law of cosines in the chat, but I'm really not sure how this applies since this is an algebra question. Yeah, but in all seriousness, there is going to be a geometric solution, but we're going to be learning how to do this question algebraically. Okay, so does anybody have any ideas? Okay, so I see a lot of pretty good ideas in the chat. So what we're doing is we're trying to manipulate the 3 equations we have right now in order to make the result. So I guess the first thing we want to do is find out what exactly the result is. So let's go ahead and expand it. So now we want to somehow manipulate these 3 equations to make what we have right here. So probably the most annoying term in this expansion is going to be the last 3 terms, the a squared bc plus ab squared c plus abc squared. So we first want to find out a way how to, we first want to find out how to get these terms. Yeah, so you can subtract it, but we're not going to subtract it. So what we're going to do instead is find out a way to get a squared times b times c. So it looks like we can just multiply the first 2 equations because we have, I mean, let's do the last 2 equations because we have bc in the second equation and an a squared in the third equation. So let's see what that gives us. So if we multiply the second and the third equations, we get it looks like the LaTeX isn't loading. Brian, could you manually recompile it? Yeah, so this is what we get. And hooray, so we got an a squared bc term. We also got an ab squared c and an abc squared. But it looks like we also get a ton of unwanted terms, such as c to the fourth, bc cubed, and ac cubed. So we don't want these terms. But firstly, remember that all the equations we have are cyclic, and our final result is symmetric. So we want to keep everything symmetric. So in order to keep everything symmetric, we're going to first compute the product of the first and third and the first and second and add all three just to make it symmetric. Somebody asked, are the recordings going to be put on the website? And yes, you can find all the recordings on the website if you click the topic in the schedule. And once you get there, you'll find our YouTube channel, and then you can just check every week on our YouTube channel. So yeah, back to the question. This is what we get when we add all three symmetric sums together. So this is just the product of the second and third equation plus the product of the first and third plus the product of the first and second. So as you see, we have some good terms. We have a squared b squared, which we want, and we have a squared bc, which we also want. But unfortunately, we have a cubed b and a to the fourth, none of which we want. But then we remember that if we square one of the equations, we can actually get both the a cubed b and a to the fourth. So let's go ahead and square, let's say, the first equation. No, let's do the third equation. And then this is what we get. Oh wait, that doesn't work. Let's actually square the first. So this is what we get. And as you can see, now we have a cubed b and a squared b squared. So if we do what we did before, namely find the other two expressions and add them all, yeah, this is pretty bashy. This is what we get. And now can anybody see how to eliminate all the terms we don't want? Namely the a to the fourth plus b to the fourth plus c to the fourth and the a cubed b plus b cubed a plus dot dot dot. So what we're doing right now is just we're expanding a lot of stuff. So the top equation is us expanding the product of the first and second plus the product of the first and third plus the product of the second and third. And the bottom one is us expanding the sum of the first one squared plus the second one squared plus the third one squared. And right now we don't have any equations, we only have expressions, since we're just trying to find a way to manipulate our expressions to make the final answer. Yeah, so Kevin says divide the second expression by 2. We're actually just going to multiply the first expression by 2 since we don't like fractions. So let's multiply the first expression by 2 and subtract the second expression from it. And let's see what that gives us. So as you can see, our first expression has like a to the fourth plus b to the fourth plus c to the fourth, and our second expression has 2 times a to the fourth plus b to the fourth plus c to the fourth. So we multiply the first one by 2 and subtract the second one. All the a to the fourths cancel out. And similarly for the a cubed b terms, the first expression has a coefficient of 1 and the second has a coefficient of 2. So we multiply the first one by 2 and subtract, they also all cancel out. So actually we get rid of every single term we don't want. But it's actually even better than that, because let's look at the terms which are left, which are the terms we want. So for a squared b squared, our coefficient is 3, and for a squared bc, our coefficient is 6. You can just verify that by multiplying the first one by 2 and subtracting. But that's just 3 times ab plus ac plus bc squared, which is exactly what we want. So now we found a way to manipulate all three of our expressions to get our final answer. So let's just compute it. So once again, how we got this expression is we multiplied the pairwise products, multiplied that by 2, subtracted the sum of the squares, and then divided by 3. So we just plug in all of our numbers, and we get -11/3 minus 4/3 I, which is our final answer. Somebody asked for the motivation. So our motivation basically is we have 3 equations which are cyclic, and we want to find the result, which is a symmetric expression. So if we don't have any better ideas, the best thing we can do is just try to manipulate our equations to make the result. So the reason why we think about this manipulation trick is they actually don't ask for A, B, and C, or like something simple like A plus B plus C. They ask for AB plus AC plus BC all squared. So this hints that we probably can't find A, B, and C. And there's some clever way to convert the equations we're given to the final expression. So of course, none of this is guaranteed to work. Like when we computed the first square, yeah, Brian, could you scroll up to the second slide? So yeah, when we computed the first sum and we computed the second sum, we weren't guaranteed that when we subtracted them, everything would work out. And we weren't guaranteed that we would actually just get 3 times our final answer. But the point is this question was somehow contrived to work like this. So under contest conditions, this would be actually a feasible solution. But of course, there actually is an underlying reason. And as a lot of people have said at the very beginning of the question, this has to do with Fermat points and law of cosines. And our handout, which we will give after this class, will give a few hints on how to approach this question geometrically. Are there any more questions? Okay, cool. I guess we can go to the next question then. So this question is from Ibero-American. For all of you who don't recognize it, that's actually an Olympiad competition. Whoa. But don't be daunted. It's AME level. Somebody asked, how would a geometric solution work? So you can find this in the handout, of course, but if the complex numbers were replaced with integers, any values of integers would work, which means that there's somehow an underlying algebraic expression which we derived in this the above slides. So since the algebraic expression works for infinitely many real numbers, it should also extend to complex numbers, because in the end, the geometric interpretation is just a way to simplify the algebraic manipulation. But let's focus on this question right now. So once again, we have a few cyclic equations, except this time we're actually asked to find x, y, and z. So trying to manipulate the equations weirdly wouldn't work here. So we'll give you a minute. Okay, yeah. So a lot of people are saying expand the third. So this is a really good idea because the first and the second equations are both really nice, but the third one looks really ugly, and we can probably find a way to simplify it once we expand it. So that's the first thing we're going to do. And we get this: x squared y plus xy squared plus x squared z plus xz squared plus y squared z plus yz squared, all minus 6xyz. So is there anything nice we can do to the expression now? Yeah, substitute. So if we look at the expression right now, we actually have xyz in the left-hand side, but we know that xyz is equal to 8. Similarly, we have x squared y plus xy squared, x squared y plus y squared z plus z squared x, and we know that's equal to 73. So once you do those computations, strangely enough, we actually get xy squared plus yz squared plus zx squared is equal to 73. And if that number looks familiar, that's because it's x squared y plus y squared z plus z squared x. So we have the equality shown on the slide. So that's actually really neat. And this tells us why we were given these random numbers, actually. So does anybody have any ideas we can do to this? Well, first, let's move everything to the same side. I guess not. So yeah, as Kevin says, we can actually factor the left-hand side. So this is why knowing your factorizations is very important for competitions, because like, even though this question looks really hard right now, once we factor it, actually becomes really easy. So if we look at the left-hand side, it's actually factorable as x minus y times x minus z times y minus z is equal to 0. And if you want to verify this identity, you can just multiply the, actually, do I have a sign error? No, I don't have a sign error. So if you want to verify this, you can just multiply the top equation. You can just multiply the bottom equation and you'll see it gives the left-hand side to the top. So what does this tell us? It tells us that two of the variables are equal since one of the factors is equal to 0. But since everything is symmetric, cyclic, we can just assume that x equals y, because why not? So x equals y, and now let's just plug back into our original equations. So the first equation becomes x squared z equals 8, and the second equation becomes that x cubed plus x squared z plus z squared x is equal to 73. But since there's an x squared z inside and we know that's 8, we have x cubed plus 8 plus z squared x equals 73. So after we notice the substitution, this factorization, the question as a whole becomes pretty routine. We just solve normally. So if we try finding z in the second expression, we get z squared is equal to 65 over x minus x squared. And then now square the first expression and plug z squared into it. And it's easy to verify that you'll get 65x cubed minus x to the 6th equals 64. So do we know how to solve this? Yeah, this is just a quadratic in x cubed. And not only is it quadratic, it's a factorable quadratic. And we'll get that x cubed is either equal to 1 or 64, which means that x is equal to 1 or 4. And then we just plug it back into the initial equation to find z, and we're guaranteed that it works. So our final solutions are 1, 1, 8, 4, 4, 1 half, and cyclic permutations. What that means is that we could also have 8, 1, 1 because we will log that x equals y. So are there any questions for this one? Okay, I guess not. So we'll be moving on to the final question of the day.
Yep. So unlike the systems and multiple equations that we were dealing with before, right now we have just a single equation in one variable, and we want to find x. So I see people are already suggesting substitutions and all this, but if we take a look at this equation first, on the left-hand side, we have fractions of the form n plus over x minus n, 3 over x minus 3, 5 over x minus 5, and so on. So yeah, if we add 4 to each of these, we can make all of the numerators the same. And this would probably be convenient. And conveniently enough, if we have a 4 on the other side of the equation, that goes away when we add 4 to the left side. So yep, each term on the left-hand side is n over x minus n. And we add 1 to get x over x minus n. And when we do that to all of the terms, we get an equation that looks like this. And this is great because there's a factor of x on both sides. Now, we want to divide by x to make the equation simpler, but we need to be careful because that could get rid of the solution x equals 0. But x equals 0 isn't going to be the largest solution to the equation, so we can divide without any worries. So let's divide that out. Now we're faced with this still scary looking equation. If we want to multiply by a 4th degree polynomial, then we're going to end up having to solve a quintic. So instead, let's take a look at the numbers on the left-hand side, 3, 5, 17, and 19. They all happen to be symmetric around 11. 3 and 19 are symmetric around 11, 5 and 17 are symmetric around 11, and there's 11 and 11 on the other side. So yep, let's substitute y equals x minus 11. And when we substitute y equals x minus 11, we get this equation. And this looks a lot cleaner because we have minus 8 and plus 8, minus 6 and plus 6. So let's put the minus 8 and plus 8 into one fraction, and the minus 6 and plus 6 into another fraction. If we do that, we get, let's see. We'll continue on the next slide. We combine the y minus 8 and y plus 8, and that gives you y squared minus 64. And we combine y minus 6, y plus 6, and that's y squared minus 36. So now we have y's on the top again, and we want to divide by y, but we just need to be careful. We don't want to lose any solutions here. So we'll just keep in the back of our minds that y equals 0 is a solution and try to see if there's any other bigger solutions. So if we divide out by y, we get 2 over y squared minus 64 plus 2 over y squared minus 36 is 1. Now you could solve it right here, solve it directly for y squared. But if you let z equals y squared, it looks a little nicer. It's not harder to solve if you don't make this substitution. So now this is just a quadratic if we multiply out by both sides. And that should be easy to solve. Multiply. Scroll down, please. Yep. So now we get a quadratic for z. Oops. That should not be z equals z squared minus 1 over 4z. Let's fix that. Yeah, so now we just get a quadratic for z. And these two solutions are 52 plus or minus the square root of 200. The larger one is 52 plus the square root of 200. So y is going to be the square root of this thing. And this is more than 0, so this is going to be our largest solution. Now we just have to add 11 to get x. And this nasty radicals inside radicals is then our solution. And yep, if we want to do the answer extraction, then it's 11 plus 52 plus 200 equals 263. What if x equals 11? Yeah, x equals 11 is a solution, but it's not the largest solution. We just want the largest solution. That's why we were careful to note that x equals 0 and y equals 0 were solutions, because when we divide by a variable, that we can lose a solution if that variable happened to be 0. Yep, there are multiple solutions to this. There should be 6, because it's a 6th-degree equation. Yeah, the solutions would be 0, 11, and 11 plus minus the square root of 52 plus minus square root of 200. It said that in the problem statement. It might have been blocked a little bit. Yep, we want the largest real solution. Well, with this approach, it's not too hard to find all solutions. You can just change the pluses in our radicals to plus minus, and the other two solutions are 0 and 11. So that looks like it's wraps for today. Ended on a tricky problem.
Yeah, thanks everybody for showing up. The handout will be posted soon.
So the handout, I sent it in the chat.
Oh, the handout actually is already posted. So yeah, once again, make sure to fill out the feedback form if you haven't. It's optional, but it'd be great if you could so we can make this class better. And sorry for technical difficulties today. We're still trying to get used to our new system.